All right. One of the things that we learned when we were using absolute value, even before that with linear functions, is the way you choose your input values can really save you time in graphing. It can really help you with getting good output values. But we haven't had a lot of experience with quadratics. At this point, let's just try to use what we used with linear. So with linear, we usually put 0 in the middle. And we just picked 1 and 2 in the positive and negative direction. So I would have positive be my top, negative directions. Make sure you have the same order I do. And that way this would fit on a number line, right? They're in order from greatest to least. Right? So I can just pick inputs and then just evaluate in order. So I can plug in 2. So if I plugged in 2, we'd have 2 minus 7 and 2 minus 1. 2 minus 7 is negative 5 times 2 minus 1 is 1. So this would be negative 5. Right? And I can erase it if you guys are working on scratch paper. Right? You don't necessarily need to erase it. You're just going to write the second time. So now we're going to plug in 1. Right? So I have f of 1 and plugging in 1. Right? If I plug in 1 in place of x, well, 1 minus 7 is negative 6. 1 minus 1 is 0. Negative 6 times 0 is 0. All right, this next one we have to be careful of, because if we've spent most of our time with linear functions, we're expecting to plug in 0 and get out 0. But we actually have two x values to input for. So I have 0 here, 0 here. That just means that this factor is negative 7, this factor is negative 1. Negative 7 times negative 1 is positive 7. All right, so that does not have an output of 0, even though that might have been what we were anticipating. All right, I'm going to plug in the last two inputs. So I'm going to plug in negative 1. Negative 1 take away 7 is negative 8. Right, we're going in the same direction, so the larger negative. Negative 1 take away 1 is negative 2. Again, we're going in the same direction. So larger negative. Negative 8 times negative 2 is 16. All right, this isn't going to be a useful point for us because 16 doesn't even fit on our graph. So that's not very useful. So that wasn't a very good choice. There are ways to try to prevent against that. We haven't learned it yet. So we just realized, oh, that one's a bad choice. It's actually going to get even larger as we plug in negative 2. So this is going to be a bad choice as well. So I have negative 9 times negative 3, which is 27. So choosing the way we chose for linear functions, so far not so good, because I already made 5 choices. Only 3 even produced outputs that fit on my graph. 2, negative 1, 2, 3, 4, 5. I have 1, 0, and 0, 7. Which if I was just looking at this, I might just think, oh, this is a line. And I'm like, okay, done, line, good, over with it. All right, so this would be a bad example. So I'm going to call it a non-example. Don't do this. This is bad. All right, but sometimes to understand why something is good, we have to first learn why doing something else does not work or is bad. All right, so this is a non-example. You don't want to just pick 0 and pick numbers going out from there. All right, I could have continued to pick values, but this method is not going to be very helpful. All right, it doesn't give me a very full picture. I only had 3 points that worked, and of the 3, it kind of still looked like a line, but you can kind of see that the distance there versus the distance here isn't the same. All right, so let's try it a different way. All right, now this is built on anticipation, and we might not know a lot about choosing inputs, but we should know the basics of what a quadratic looks like. We know it's either a parabola, which is that U shape facing up, or it's a U shape facing down. All right, if we look at the previous example, we thought it was a line because we never saw where it changed direction. All right, so that point that's changing direction, that pivot point, or that critical point, that important point, that's called the vertex. All right, which we call the vertex like the corner of different polygons. It's kind of like a corner. But the vertex for a parabola or an absolute value would be that point in which it's changing direction. So the vertex is very important. So let's just, I don't know, guess where a parabola could be. Let's pretend there's a parabola here. All right, the most important point right? We have the vertex here, right? That's the pivotal point. So I want to make sure that's in the middle of my table, and then points going from there, right? That should be in the middle, and it should just be going outwards from there. The question is how do I know where that's going to be? Well, I do know that if this was drawn to scale, right, this would be symmetrical. This spot and this spot would be the same distance away. Same as this spot, and so on and so forth. All right, now, of all of those different spots that are the same distance away, the x-intercepts are very easy to find, because x-intercepts are when you're on the x-axis, specifically when your output is 0. All right, so we know that these occur when our output is 0. And the vertex should be halfway in between those two spots. So if I can find my two x-intercepts, I should be able to find my vertex. And then I can pick the rest of the points going from there. So let's do that. All right, well, my x-intercepts, that's when we said this would be equal to 0. Oops, got my magic pen tool on. All right, so it's when it's equal to 0. All right, which is very important when solving, because something having a product of 0, there's only so many possibilities. If you picked any two numbers in the world that multiplied to 0, I can guarantee to guess one of them. One of them is 0. You can pick 1,000,000 and 0, 100 and 0, 2 and 0, negative pi and 0. One of them has to be 0, 0 and 3. So one of those is 0. So we have two cases, right? So case 1 is, well, what if x minus 7 is 0? Well, if x minus 7 is 0, x would have to be 7 to make that statement true. Right? If I add 7 on both sides, you get x equals 7, because 7 minus 7 is 0. Or I have case 2, where x minus 1 is 0. I can add 1 on both sides, or I can just see that 1 minus 1 is 0. Right, and I'm going to put that here. So I have my x-intercepts. I got 7, 0, and 1, 0, which would show up in my graph right here at 1, 0, and 7, 0. The vertex is halfway in between. I can count and find the halfway point, or if I wanted to do it numerically, I just add those two numbers together and divide by 2. If I do 1 plus 7 divided by 2, well, that's 8 over 2, which is 4. All right, 4 is going to be that middle point, or the vertex, because 4 is 3 spaces away from 7 and 3 spaces away from 1. So I know it's somewhere on this axis, right? Somewhere where x is 4, the vertex lies. It's either above it and curling down, or it's below it and curving up, but I know it's somewhere at 4. But now that I know that's where it is, it's in the middle of my table. And now it's in the middle of my table, I can pick points that'll be between the vertex and the x-intercepts, and I'll be able to pick points outside of the x-intercepts. All right, so a number between 4 and 7, let's just go with 5. All right, between 4 and 1, we can say 3. After 1, let's just say 0. And after 7, we can say 8. But now we've picked inputs that guarantee that the vertex is in the middle. We also guaranteed that these spots are the same distance from the vertex. So these are both 1 away from 4. These are both 3 away from 4. That's why they're both 0. These are both 4 away from 4. So all of these spots should be the same numbers relative to one another. The last two spots should be the same. Right? Our x-intercepts have the same outputs. 3 and 5 should have the same outputs. And 4 should be the only unique output. Right? And that's our vertex. So let's label that real quick. This middle spot here is our vertex. Just so we don't forget, because it's hard to remember those new words. All right, so that's our vertex. All right, and we didn't get that first. That was our goal. But in order to achieve our goal, we had to find these 2 points on the x-axis, which we should be familiar with what those are called. That's the x-intercepts. All right, so these 2 points right here are your x-intercepts. All right, we knew that an x-intercept, if it's on the x-axis, all right, if it's here, well then the output has to be 0. And that let us find, oh, that has to be 7 and that has to be 1. Alright, the rest of the way we're just evaluating like we were doing before. So, I'm going to erase real quick. Yeah, we're going to evaluate the rest of those points. So if I plug in 8, right, well, 8 minus 7, and 8 minus 1, well, 8 minus 7 is 1, 8 minus 1 is 7, 1 times 7 is 7. Alright, we also saw from our previous table, this was 7. Alright, if I plug in 0, that's negative 7 times negative 1. Negative 7 times negative 1 is 7. Alright, 3 and 5 should also be the same. So if I plug in 3, right, 3 minus 7 is negative 4. 3 minus 1 is 2. Negative 4 times 2 is negative 8. Alright, and that's going to be the same for both of these, and I'll show it in a second. Alright, but if I replaced these with 5s, watch what happens. Well, 5 minus 7 is negative 2. Alright, so that number right there is negative 2, and the other one's going to wind up being 4. So they really just wind up switching spots and switching signs. So 5 minus 7, I get negative 2. 5 minus 1, I get 4. Negative 2 times 4 is negative 8. Alright, so that's just showing that these two are the same. Vertex is our only unique point. That's the point which is changing direction. So we still have to plug in 4. Alright, so if I plug in 4, 4 minus 7, 4 minus 1, 4 minus 7 is negative 3. 4 minus 1 is 3. Negative 3 times 3 is negative 9. Alright, and that's the vital point, the critical point that shows a change direction. So if I go to 4, well, negative 9 is just 1 from the very bottom, so 1, 2, 3, 4. 1 from the very bottom. There's my vertex. Right, that's the point where it's switching. Alright, I'm going to put the other ones in black. So then I have 3, negative 8, 5, negative 8. So there's just one above where negative 9 is. So that's 5, negative 8, 3, negative 8. Then we have 1, 0. And we have 7, 0. And then I have 0, 7. And I have 8, 7. Alright, so let's split screen and look at the difference by picking good results. Well, here's our non-example, which isn't completely wrong. It's just that we didn't pick enough points. We didn't even see what the rest of the picture looked like because we didn't know where to pick them. Whereas this, we can now see that special shape that's, you know, it's like a stretched out V, or a lot of times they say U-shaped, but it's a parabola. So now all I have to do is try to draw a smooth curve, which I'm going to struggle with my mouse. Hopefully you can be better with pencil. Alright, I've formed my parabola. I can see how my non-example produced something that looked like a line. So a lot of times you can evaluate all your inputs correctly, but if you pick bad inputs, you're going to get something bad like that on the left. Whereas choosing good inputs, right, I'm guaranteeing to make this process faster. There's a lot of self-checks built in. And so you want to make sure to be able to find your x-intercepts so that you can get your vertex and then pick points that are equidistant from the vertex so that you get this nice symmetrical parabola. Alright, that's it.